there are no participants, I think. No?
They are joining, sir. They are joining, and at 2 o'clock only the count will increase, sir.
Okay.
So very good afternoon to all. It's a pleasure to welcome you all again for the one week FDP on purely the fundamentals of mechanical engineering, and it is third day, sixth session. The Chennai University of Technology has been taking tireless effort in enhancing the knowledge of faculty members, research community, and students community by conducting Knowledge 4.0 webinar series. Knowledge 4.0 webinar series is one of the unique and distinct initiative of Chennai University of Technology under the guidance of our Honorable Chairman, Sri P. Sriram, who is one of the well-known first-generation entrepreneur, Managing Director of MK Group of Companies. Under Knowledge 4.0 webinar series, we have been conducting webinar series like Technical Webinar Series, Research Webinar Series, Career Guidance Webinar Series, and Innovative Talk Webinar Series. Along this series, we are also conducting international workshop, international seminars, and national and international conferences and faculty development programs. Today, we are in the third day and sixth session of faculty program, and the particular session is going to be handled by Dr. P.Kaushik, professor from NIT Trichy, and I welcome him for the wonderful session, sir. And it's my proud to introduce him and welcome him, since Dr. Som and Dr. Sumar Chakravarti are the legends of fluid mechanics in this scenario, in this century, and Dr. Sumar Chakravarti is a living legend of fluid mechanics in this scenario, and it is I feel very happy, since Kaushik sir had worked with and Dr. Sumar Chakravarti and Som. It is our pleasure to welcome you again for the particular this session, sir. And Chennai University of Technology was established in the year 2010 by our Honorable Chairman Sri P. Sriram, and now it is being within top 10 among all private engineering colleges in Tamil Nadu, even though it is very younger institutions. So it is my proud to welcome all the participants once again with the Dr. P.Kaushik, and I request Ms. Supna Sai to introduce our expert, Dr. Kaushik sir.
Good afternoon, everyone. Myself, Supna Sai, pursuing second year mechanical engineering in Chennai Institute of Technology. Today is our chief guest, Dr. P.Kaushik sir. Dr. P.Kaushik is an assistant professor at NIT Trichy, did his BE Mechanical Engineering from VTU, Belgaum University, Karnataka in the year 2009. He did his MTech in Thermal Science and Engineering from IIT Kharagpur in the year 2011. In 2017, he received his PhD from IIT Kharagpur. His areas of research interest includes fluid dynamics, computational fluid mechanics, non-Newtonian fluids. He has also published more than 20 journal articles and 2 conference papers. We are very glad to have you here, sir.
Thank you very much, sir. So maybe now I can start.
Yes, sir.
Very good afternoon to everyone, and today I think we're going to discuss regarding fluid dynamics. I am not sure how to give the fundamentals of fluid dynamics in this time described. So he said that maximum 1.5 hours. So I'm not sure of how much I can give you, but what I thought was rather than giving lot of information about many things, we'll concentrate on a few aspects which usually the students find little bit confusing or sometimes difficult, and we will discuss those aspects. And of course, if you're interested in further, uh, reading or something, I can suggest some material also. So the idea is that those aspects which are little difficult to understand, that we will try to simplify a little bit today, and then as teachers, I think all the participants here are teachers. You can slowly, inculcate those things to your curriculum, and you can read many better books of fluid mechanics which are more complex and you can understand better. So based on that, let us start. So I will start sharing my slide, and slowly we will go about this. If you have any doubts or something, you can definitely, I think there's a chat option, I suppose. You can ask in that. Uh, if anything, you can also mail me later on. Okay. Okay, I hope all of you are able to see the slide. Okay, so
Yes, sir. Yes, sir. You can go ahead, sir.
okay, thank you. So I have not made a very long presentation, and since fluid mechanics always goes hand in hand with mathematics, so there are quite a bit of equations. I have reduced them or simplified them to give it in a very simple way. But without that, I think explaining fluid mechanics is very, very difficult. So when we talk about fluid mechanics, this word mechanics is what comes in. This word mechanics has a very classical meaning. So you know that in our high school we have physics, we have studied that mechanics. So let us start from that point, and we will go to what is fluid mechanics. So this is my overview. So let us start with what is this continuum mechanics. So if you can see my slide, you can see that continuum mechanics is what we normally study as classical mechanics. So continuum is the concept where we assume that the medium or the material is a continuous object, and we study or we define everything based on that. So there are two parts in continuum mechanics. So on the left side, you can see that it is solid mechanics, and on the right side, fluid mechanics. So solid mechanics also mechanical engineers study in terms of strength of materials and such other subjects like engineering mechanics, strength of materials, etc. And on the right side is what we will deal with today, fluid mechanics. So as you know, that mechanics in general has two parts. That is, one is the statics and the other one is the dynamics. So this is well known. This is for solid mechanics also as well as fluid mechanics. So fluid mechanics has fluid statics and fluid dynamics. So based on these two important parts of fluid mechanics, I thought that I will give a brief overview of each of them. Okay, and how mathematically we can go about it with a very small example in each case. So let us see how we can deal with fluid statics. So now when I go into that, you will see that there are some equations that are involved. Don't worry, I will try to explain those equations, and it is not very complex as you may think. So in continuum mechanics, okay, there are two types of forces. Okay, one is called the surface force, and another is the body force. Okay, so this is true for both solid mechanics as well as fluid mechanics. This is very simple to understand actually. So surface force, and it is sometimes called as contact force, can act either on the bounding surface of the body as a result of mechanical contact with other bodies, or on imaginary internal surfaces. So if you have a continuous body, you can take a section and you can do a free body diagram, and in that you can have forces on the surface, and that is why it is called as the surface force. Similarly, there is another type of force that is which acts from outside the body, and it acts on the volume of the body or the bulk of the material or the continuum, and that is called as the body force. For example, if you have, say, your any paperweight, that the gravity force acts on the paperweight over the entire mass. Okay, so volume or mass here we are using interchangeably because it is the extent on which this force acts. So these two are the two main forces that you normally encounter in continuum mechanics. So how it is expressed and how they are managed also slightly varies. So surface forces are usually represented in terms of force per unit area, and in general in solids we represent them by your regular stresses and sometimes pressure. These are all surface forces, and body forces are usually in terms of volume. So body force we many times write it in terms of per unit volume, etc. So there are a lot of details of this in many continuum mechanics books, but today we will just see basically how these are managed in a very simple format. So evaluation of surface forces. Okay, so there are many equations, and a fluid mechanics traditional lecture is very difficult to give in slides. It would be actually very easy in a board, but anyway, I try to give some board feel on the slide itself. So suppose you have, if you want to evaluate the surface force and you have this body, which I can divide by this section, and at point P, I want to find the surface force. So let us say you take the free body diagram of this one and put it on this right side, and let us say at point P there is a surface force delta Fs which acts on 1 because of 2. Okay, so that is why Fs12, and this dash over that means it's a vector. Force is always a vector, and this surface has an area delta Ax. Okay, and the coordinate systems are chosen in such a way that you have the x and y direction, and which has the unit vectors I and j. So we can write Fs12 as delta Fsxi. Okay, there should be a plus sign, plus delta Fyj. So this is the how you give the two components. So the two components are given here in the dashed line. So the x component and the y component. Okay, this is a very simple vector resolution of force. So your surface force is not it's still a force, but when you want to write it in terms of the stress vector, which is a per unit area. So we said that this force is always given as force per unit area. So that is the usual units. So if we write the stress vector in the ith direction, Si, we can write it as limit delta x tends to 0, delta Fs12 divided by delta Ax. So Ax is the area on which it acts, and we want to bring it down to a single point. So why we do that is that way we define the stress at each individual point, and if we integrate it over all the points, we will get the entire stress force. So that is why we bring it down to 1 point. So if you see limit delta Ax tends to 0, delta Fs12 by delta Ax is how we define. So again, delta Fs12 we can split into two parts. One is the x part and the y part. So that is what we are doing in the next step. And so one is the x component and another is the y component. So the x component we write it as sigma xx, and the y component we write it as tau xy. So this tau xy actually is written in such a way that the first letter, that is x, is the direction outward normal of the plane on which this force is acting. So stress has to be defined based on the force direction and the direction of the plane. So the plane on which it is acting is the x plane. That is the outward normal of the plane. And the direction it is acting is in the y direction. So if you see in the previous slide, Fsy is in the y direction. So you see the components. And the xx is in the x direction. So it is acting on the x direction along the x direction plane. So that is why xx. So this is how we get the stress vector, okay, as components of this regular stresses sigma xx and tau xy. So this is for a 2D case. You can definitely do this for a 3D case. It is not a difficult thing. It's just a simple extension of what you have here. So once we have this, so we can get the stress vector of a fluid at rest. So if you have this 1 and 2, these free bodies, the stress that is given or acting on 1 because of 2, if it is given as sigma xx, then the stress acting on 2 because of 1 will also be sigma xx. Why? Because of Newton's third law. And so since these two are equal, we can write that the stress I is sigma xxi, and the stress vector of minus I is minus sigma xxi, which is minus of Sm. So this is like it comes from Newton's third law of motion. So this gives you actually the sign convention of the what do you call the stress vector. So how it will be in each direction. So this is common for even fluid mechanics and even solid mechanics. So till now we have not especially talked about fluid mechanics. We have just taken a body and we have split these stresses. So we will go to the concept of a fluid after a couple of slides. So anyway, we will discuss this tensile and compressive stresses. These are all well known actually. For whether it is solid or whether it is fluid, this is true. So if sigma xx is greater than 0 or outward pulling effect is there, then it is a tensile stress. And if the sigma xx value is less than 0, then it is compressive. So this we know very well, and this is common for solid as well as fluid mechanics. So what is different in fluid mechanics? So that is very important to understand. Continuum mechanics, all these points are true. How we define stresses, how we define all this tensile, compressive, etc. So how do you find stress on an arbitrary surface? This is the next thing we'll discuss. So we know that there are regular stresses, sigma xx, tau xy, etc. So on an arbitrary surface, how will we find the stress? So let us take a wedge. The wedge is like this, OAB. So OA is along the x direction and OB is along the y direction. And AB is the unknown direction, which is at an angle theta with the x-axis. And the unit outward normal is n. So I can write this n vector as nxi plus nyj, the two components in the x and y direction. So nx, we can write it as sine theta, ny is cos theta. Here, because this is a unit vector, so therefore the magnitude is 1. So that I've shown in the bottom line here, where n magnitude is 1. So if sigma xx is acting on OB, then sigma yy will act on OA. That is what we see in this field bar detail. And this unknown sigma nn is acting on AB. So what is the relationship between these? So if I say that the fluid is at rest, okay, this OAB is at rest, then the net force that is acting on this will be 0. If it is 0, then each component, that is sigma fx, will be 0 and sigma fy also will be 0. So the x component, if it becomes 0, so you see it will be minus sigma xx ax plus sigma nn an sin theta equal to 0. So this is what we get. And we know that an sin theta is ax, because from the geometry itself, we can make out that an sin theta is ax. Okay, so once we get that, we can just divide the entire equation by Ax and we get sigma Nn equal to sigma Xx. Okay, so then balance of stress in the y, the forces in the y direction. So how do we balance the force in the y direction? Similarly, we can do this. But here you have to remember, in the y direction, there is a gravity force that is acting. Apart from the surface force, there's a body force which is in the y direction. So normally we take gravity in the downward direction. So here I'm assuming that gravity is there only in this y direction. So the sum of the forces in the y direction, it can be written as sigma Nn An cos theta minus sigma Yy Ay minus mg. M is nothing but the mass of this body OAB into the g. That is the force. Mg will be the force. And the net force is 0 because it is at rest. So remember that sigma Nn component along the y direction will be the positive y direction, whereas sigma Yy and mg will be in the downward direction, that is negative. So that is why this plus and minus sign come. This is from classical mechanics. So we are not doing anything very complex. Only thing now we are writing is m is instead of writing it as m, which we do in solid mechanics, here we are writing as density into the volume, rho into v. So again, An cos theta is Ay because that is from geometry. So you can get sigma Nn plus equal to sigma Yy plus rho gv by An. So, so this is what we are getting. Now, if we have to bring it down to a point, so what we do normally in Pascal's law, we say that the pressure acting in all directions is the same. All direction is the same. That is like a vague way of saying it. So actually, at a point, it is only at a point that pressure in all directions is the same. So obviously, this OAB is a finite sized thing. So it is not just a point. So we have to bring it down to just a point. So how we do that is, see, when you make it smaller and smaller, so I'm showing this with dashed lines of this wedge. So the angle still remains the same. Only thing, the size reduces. So to limit, the volume tends to 0. That means the surface area also will tend to 0. But limit volume by surface area, will it tend to 0 or not? That is the question. So if volume is tending to 0 and surface area also is tending to 0, which will tend to 0 faster? It will be the volume, because the volume is of the third power, whereas surface area is of second power. Suppose you have the surface area as 1 and volume will be 1 cube. If the length is 1, then area is 1 square and volume is 1 cube. If you reduce the length to 0.1, the volume will be 0.1 cube and area will be 0.1 square. So 0.1 cube will be 10 power minus 3, whereas 0.1 square will be 10 power minus 2. And so if you keep reducing it, volume will go down faster to 0 as compared to area. So therefore, limit V by An tending to 0 means the volume will go faster, and therefore that value will become 0. Therefore, when you bring it down to a single point, we can write that sigma Nn equal to sigma y. So sigma Nn equal to sigma xx equal to sigma yy equal to sigma zz. If you want, you can do it in the z direction and add the sigma zz equal to minus b. This is true when all taus are 0. So how we did this? So let us go back. So here we have the stress is sigma xx plus tau xy, sigma xxi plus tau xyj, and then I took this. Here I removed the tau, and without tau I proceeded. Why I removed tau is because here I am writing the stress vector of a fluid at rest. This at rest is very important. So this is where your definition of fluid comes. So fluid is defined in such a way that if there is a shear stress within the fluid cannot resist it. So it will continuously deform when there is a shear stress. If it is deforming, that means fluid is not at rest. So if fluid is at rest, that means there cannot be any shear stress. So that is why this tau xy part has not been taken here. And that is how we were able to come up with this analysis. So for a fluid at rest, there is no tau. Therefore, we are getting this sigma nn equal to sigma xx equal to sigma yy equal to sigma zz equal to minus p. Since all tau are 0. If tau are not 0, then this is not true. So that is why there is a distinction between fluid statics and fluid dynamics. So this is the static part. So because the fluid is defined in such a way, so so that is how probably I explain to students. That's to see. Students will say there are many things. So normally the student will come into the second year. It's just 1 year after the high school. So they will say the definition of fluid in many ways, like the molecular forces are this one molecules are more far spread apart as compared to solids, etc. Something which they have learned in high school. But from an engineering point of view, fluid has to be defined that shear stress cannot be resisted by a fluid. So it will continuously deform on application of shear stress. And that point, with that true, if the fluid is at rest, there is no shear stress, and therefore Pascal's law holds good. So if there is a shear stress, then the fluid will start deforming, and the fluid is no more static; it is dynamic, and that is how we can distinguish the two parts of fluid mechanics, the statics and dynamics, and how we define the fluid, and based on the definition, what we are getting, the consequence. Now, now that this part is very clear, it is actually you can look at it from a very different angles. But this is one of the very easy ways to explain to a student that static fluid will not have shear stress because it cannot resist shear stress. Okay, so once we understand that, let us go to a little higher step. Then what is a pressure field? So in a static fluid, we said the forces acting are 0. So the sum of these forces should be 0 because it is at equilibrium and it is not moving. So the surface force plus body force net should be 0. Now we said that the pressure acting at a point is all equal in all directions. Okay, so that is the pressure. So pressure we give as minus P because you know that pressure is generally compressive. So and the sigmas are usually for tensile. So that is why it is minus sign. So it's just a sign convention. It is not some magic sign that has come in here. So once we understand that fluid is static, we can write the net surface force on this finitely sized body. Remember, this L and R are not the same point. Now they are two different points. In the wedge, we got it down to 0 to a single point. If you bring it down to a single point, PL and PR should be the same because the pressure has to be the same at all in all direction at a particular point. But fluid is still at rest, but the pressures are not equal at different points. So now, what is the net force that is acting in the x direction? That is PL minus PR into AX. This is the net force acting on this body. So what is PL? PL, you can write it as P of XL, YL, ZL. This is where the definition of pressure field comes. So pressure field, it is a way of expressing this quantity. So any quantity can be expressed as a field. So if you know the value at different points in a fixed region at different times, you can call it a field. Like you know the electric force at different points in a zone, or you can, if you know the velocity at different points in a fixed region in space. So x, y, z are the coordinates in the space, and time is the time at which we are considering the value. So PL, we can write it as this. So here I am not taking into account the time, because anyway it is just a simple thing. I mean, you can just add it if you want. But for now, we are just taking it as PL is P of XL, YL, ZL. Once we understand that PL is P of XL, YL, ZL, we can write the fluid equilibrium like this. Sorry. So PR, okay, it is R is delta X from L, and other coordinates are same. Y and Z coordinates are same. So PR, I can write it as P of XL plus delta X, YL, Z. Once we are able to do this, if the element we consider is quite small, then we can expand that PR in terms of PL using the Taylor series, which we are writing in the next line. So this is a mathematical way of representing some quantity in a field by another quantity which is nearby it. So that depends on the delta X. So this dot 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 are higher order terms. So higher order terms will become small if delta X is small. So delta X, the next higher order term will be delta X squared, delta X cubed, so on. So now what we can do is this PR. So P of XL, YL, ZL that we see here is nothing but PL. So PR equal to PL plus del P by del X into delta X plus so on dot dot dot. So PL minus PR is minus del P by del X into delta X. We're just rearranging the equation and neglecting the dot dot dots, which are the higher order terms. So that is for a small distance delta X, we can do that. So the net body force in the X direction is nothing but PL minus PR into AX, which is nothing but del P del X, delta X, delta Y, delta Z. So this is what we get. So similarly, we can do in the Y direction and the Z direction as well. So the net surface force, therefore, we can write it as Fs net Xi plus Fs net Yj plus Fs net Zk. So three directions. So we get as del P by del X, delta X. See here, Ax is there. Ax is the surface on which it is acting. That is the surface whose normal is in the X direction. So its size will be delta Y into delta Z. So if you take a rectangular surface, then obviously it will be like this. And delta X, delta Y, delta Z, I write here as delta V, which is the volume. So similarly, del P del Y into delta V J and minus del P del Z into delta V K. So we have got in terms of the Fs net. So limit delta V tends to 0, Fs net by delta V will be nothing but minus del P del X I minus del P del Y J plus del P del Z K. So minus I have taken out as common. This is nothing but minus gradient of the pressure. So this is how we can write the pressure distribution or the force distribution, okay, within the solid. So this is nothing but minus grad P. Then there are two parts. So surface force we have resolved for a fluid in equilibrium. What about the body force? The body force straight away mg. So m into the gravitational vector. So gravitational force vector it acts in whichever direction. Here anyway we have taken all direction into account, so we can just keep it as it is. M I write it as rho into delta V. So the volume of this body is nothing but delta V. So that is nothing but delta X into delta Y into delta Z. So rho into delta V into G. So the net force is nothing but the net surface force plus the body force. See, body force is a force that acts on the entire volume. It need not be just gravity body force. There can be other body forces like electrical body force, magnetic body force, etc. However, here we just are for the simple cases, normally it is only the gravity that is acting on it. Okay, so if there are other body forces, definitely it can be incorporated into this and has to be considered. But as an example, we are just taking that only gravitational body force is present and we are using only that. So the surface force plus body force we get as minus grad P into delta V plus rho delta V into G. So this we get as minus grad P plus rho G into delta V equal to 0. 0 is because the fluid is at rest. Therefore, since the volume is non-zero, so something into volume is 0, that if since volume is non-zero, the other quantity has to be 0. That is why we are getting grad P plus rho G equal to 0. If volume was 0, then obviously this can be any value, the grad P plus rho G. That could be any value. But we know that the volume has to be non-zero because it is a finite volume that we are taking. So therefore, minus grad P plus rho G is equal to 0. And this is the basic equation of fluid equilibrium, grad P equal to rho G. So you might have come across this in many standard textbooks and many other cases. But this is how it is obtained in a very simple way. So it is not very complex, and this equation is actually quite powerful. There are many problems that can be given to students with just this equation. So let us see one example, maybe not a problem, but an example of how we resolve it, say the gravity force and say is in the z direction. So we say that, okay, let us assume that gravity force is has three components in the x, y, and z direction. Okay, it is just arbitrary oriented control volume, coordinate system. So grad P equal to rho G. So del P del X, I can write it as, so here rho is we take it to be a constant. So del P del X, see grad P is rho G means this grad P has three components. So here del P del Xi, del P del Yj, del P del Zk. And G has three components. So we can equate the components. So we get that del P del X is rho Gx, del P del Y is rho Gy, and del P del Z is rho Gz. We are just equating the components of a vector like we used to do in mathematics. Once we do that, so del P del X is equal to rho Gx. So I can just integrate this equation. So if I integrate that, I get P equal to rho Gx, okay, plus some function of y and z. So if we partially differentiate this quantity, we will get back that del P by del X equal to rho Gx. So this P, if I differentiate in terms of y rather than x, so I should be, if I differentiate this P with y, I can get del P by del Y equal to rho Gy. So what is del P by del Y? Del P by del Y, see this term, the rho Gx term, that cannot be differentiated with respect to y, it will go to 0. Therefore, we get partial derivative of f1 with respect to y is equal to rho Gy. So now we can get f1 by integrating this rho Gy. So f1 equal to rho Gy plus f2 of z. Because when you partially differentiate with respect to y, we will get back the previous equation. Of course, the x cannot be there because x has already been taken care of in the earlier integration itself. So P we get as, P is nothing but P equal to rho Gx plus F1. So F1 is rho Gy plus F2. So rho Gx, rho Gxx, rho Gyy plus F2. That is P. Now we can differentiate this with respect to Z. The first term, the rho Gx term, cannot be differentiated with respect to Z. It will go to 0. And rho Gy term also will go to 0. So we get del P by del Z as dF2 by dZ. So see the difference. Here we have used the partial derivative, whereas here we are using full derivative because F2 is a function of Z alone and not a function of X and Y. Therefore, we can use the full derivative. So we get del P del Z equal to dF2 dZ equal to rho Gz. So I can just integrate F2. F2 is nothing but rho Gzz plus C. So this is our regular integration. So we can get P as rho Gx plus F1, which is nothing but rho Gxx plus rho Gyy plus F2. So rho Gxx plus rho Gyy plus rho Gzz plus C. F2 is rho Gzz plus C. So this can be done only if density is constant. If density is not constant, then we cannot integrate like this, obviously, because then we have to consider the variation of density with respect to x, y, z also. But when density is constant, this is absolutely fine. So there is another way of seeing this. Remember, in our pressure field, this is our pressure field. P is nothing but P of x, y, z, and t. So I can write dP. So if I forget the t, just x, y, z, I can write dP, the full derivative of P, as del P del x dx plus del P del y dy plus del P del z dz. This is based on the calculus. This is from simple mathematics which we study in our first year of engineering. Once we have this, so you know that del P by del x is nothing but rho gx, del P by del y is nothing but rho gy, and del P by del z is rho gz. So I can take the, see, since rho g etc are constants, I can take the d out and write as d of rho gxx, rho gyy, and rho gzz. And this I can take it to one side and write it as d of p minus rho gxx plus rho gyy plus rho gzz. This is equal to 0. Right? So once we have that, we can integrate on both sides. So integral of d is nothing but a constant on the other side. So p minus rho gxx plus rho gyy plus rho gzz is equal to c, which is a constant. So this gx and gy plus gz, I can write this g dot r. So g, we know the vector, that is gxi plus gyj plus gzk. And r is nothing but xi plus yj plus zk. R is the vector or the direction vector of any point at which we want to evaluate this. So that way we can find what is the change in pressure. So pressure at a point we can write as rho g dot r plus c. Now pressure distribution in a fluid at rest. So let us take a particular case where the g acts on the negative z direction. If g is acting on the negative z direction, then what we get? So we can write g as minus g of k. Other components gx and gy will be 0. Okay, so gz is, I write as g and g of k. So we get p as minus rho g dot r. So g dot r, since gx, gy is 0, only you get gz into z. So which is minus rho gz plus c. So this is true when fluid is at rest and density is constant and this gravity is in the z direction. So with this we can evaluate. So let us say if at z equal to 0, pressure is 0, then c will be 0. If say at z equal to 1, it is atmospheric pressure, then you have to write c as atmospheric pressure minus rho g something. So this equation can be easily used to find the pressure distribution in the fluid at rest. Okay, so this is how we actually deal with the statics of a fluid. So in the statics of a fluid, we must always remember that the tau values are always 0. So the shear stresses cannot exist. If it exists, the fluid cannot be static. So that is a very important consequence or concept that you have to understand. And based on that, we can do any sort of manipulation, any sort of derivation, knowing that truth that fluid at rest cannot resist any shear stress. So this is the part that I wanted to talk about in statics. So main definition of a fluid, how much it influences how we analyze a fluid is so important, because just by defining that fluid is at rest and it cannot resist shear stress, this tau part is completely gone. And we directly, without the tau, we directly do our simplification and further processing of the entire fluid at rest. So in our fluid mechanics, normally fluid at rest is one of the very first few topics that we define. So first we define what is a fluid and all some of the properties of the fluid, and then directly we go to this fluid at rest, and we derive the Pascal's law, etc. So we derived the Pascal's law, and we showed that this is a very important consequence, that tau xy has to be 0 for a fluid at rest, and then only the remaining things are true. Okay, so now if we have to discuss the fluid in motion, okay, if we have to discuss the fluid in motion, then what should we do? Normally, in our high school, the students actually they talk a lot about this projectile. Projectile motion is very seriously discussed in both physics, mathematics, etc. Especially, I am not sure about many state boards, but definitely in central boards and many of the standard boards in India, the projectile motion is discussed. In projectile is in high school the teachers will explain that projectile is like a stone that you throw, and the stone how it moves and what is the path it follows, and that is called the trajectory and all those things. So we are always accustomed to this understanding of mechanics in terms of particles, like rigid body, particle. These are all some of the terms that are very commonly used for mechanics in high school. So rigid body, particle, and all we understand. But when we have to do this analysis for a fluid, okay, at rest it is fine. But when it starts moving, what is moving? What is moving? The fluid. Whether the fluid is like a bulk moving, or whether it's like a particles which are moving. So many things. The molecules of fluid are of course moving, but we are not going into the molecular approach. So in our continuum mechanics, classical fluid mechanics and classical continuum mechanics, we take the fluid to be a continuum. So when it is taken to a continuum, yet there is something called as fluid particle concept which is introduced, and most of the students are always confused about this concept. So let us see what this concept is. So concept of a fluid particle. Okay, so this I have taken from a journal paper. Okay, so I am directly quoting from the journal paper. The most common definition of a finite fluid particle is that of a limiting volume of fluid throughout which physical quantities associated with fluid will be spatially uniform. So now, when we say fluid particle, especially in kinematics, we say that the fluid is, it is translating, it is deforming. If it is deforming, that means it is a finite size thing. A point size thing will not deform, isn't it? So how is that particle, whether it is finite or whether it is just a point? So finite, see, concept of a fluid particle is that it is a finite fluid particle in terms of physical quantities being the same. That means within the fluid particle, you will not see the density is changing or any other quantity is changing. It is spatially uniform. That is the concept of a fluid particle in terms of finite fluid particle. At the same time, fluid can also be seen like an infinitesimal point fluid particle. It is like how we see the whether something is like a particle or a wave. So dual nature of matter in physics. Similarly, we use this infinitesimal or point fluid particle also. Concept of infinitesimal fluid particle requires us to model the fluid as filling, one might say mathematically rather than physically, a delimited region of liquidity space of 3 dimensions. This idealized fluid is called a continuum. Its use corresponds to the disregard for atomic molecular structure of matter, with its plenty of spacing between electrons and nuclei, and even more between atoms and molecules. So we have to say that so fluid particle is something like, it is like a point where you can use your regular calculus to find the variable change between different points. At the same time, fluid particle is not a point because it has to deform. It has to it kinematics. There will be not only linear deformation, there will also be angular deformation. So if that is happening, then it has to be a finite sized. So the concept of fluid particle has to be explained in such a way that both of these are true. One is true because it is what happens in the physics. So the finite fluid particle. Why we take it as a point is because we want the ease of mathematics. So in mathematics, a point is easily defined. So when we actually talk about a projectile is usually taken as a point mass. But actual projectile may not be a point mass. It will definitely have a physical size of. If it is a stone, it will have maybe 2 centimeters or 3, whatever size of the stone is. It will have a size. So here, in concept of fluid particle, we will take both the concepts into consideration. That is very, very important. So this thing is always confusing to the student. So it is small enough so that the physical quantities are uniform within that particle, but it is not zero from a physical particle point of view, but from a mathematical point of view, the size is zero. Everything is zero. So whenever we take limit tends to zero in fluid mechanics, in my class, always students will say, "Sir, how can you take limit tends to zero? Then it will go to less than a molecule size, and how does that work?" I said, no. When we say zero, it is not a zero in terms of mathematics. It is a zero in terms of the physical nature, which corresponds to mathematics as zero. So it is not zero physically, but mathematically it is zero. So that is very, very important when you have to study the flow of a fluid. So once we understand this conception, and I urge that some of you just read this article. It is an open source article which is available. Okay, so you don't need to have any login credentials. So the reference is there. You please read it, and you will see that the author talks very clearly about how it can be explained to a student, so that the student will never get confused. So all you have to remember is, as far as mathematically you go, you can tend it to zero. But physically, that is not tending to zero. It is tending to small enough such that the properties are spatially uniform, but mathematically it is zero. So next, when we have to study the fluid flow, there are two approaches. Again, this is a very, very common thing, and it has to be explained from the very beginning when we start fluid mechanics to the students. So the Lagrangian, the Euler approach. Lagrangian approach is a very straightforward approach, and most of the students find it very, very. They understand it very clearly, especially after doing a lot of mechanics in high school. So they directly understand this. So like a projectile motion. So you just throw the stone and you observe the movement of the stone, and that is the Lagrangian approach. So individual fluid particle as it moves through the space and time. So this can be visualized as sitting in a boat and drifting down a river. Okay, so you observe each and every particle as space and time. Eulerian approach is different. That is what we have to clearly introduce during your when you teach fluid mechanics or when you start, because this is something that students don't do. Eulerian approach is the way of looking at fluid motion that focuses on specific locations in the space through which fluid flows as time passes. So you are looking at the flow in a particular zone or particular region in space. That is how, if they don't understand this, they will never understand the concept of steady state. Because in steady state, you still have velocity. That means if velocity is there, that means it is moving. Then what is the meaning of steady state? Then it is not changing with respect to time. That means the field or the view or the zone which you are concentrating, there the velocities are not changing with respect to time. So this can be visualized by sitting on a bank of river and watching the river pass the fixed location. So this concept has to be clearly explained to them in such a way that this concept of steady state comes out. So a fluid can be still moving and it can be still called steady, where partial derivative with respect to time becomes 0. So steady state means the fluid is moving, yet at a particular location the velocity does not change. Velocity is a constant. Okay, so that is the concept of steady state, and those are very important to explain. So Lagrangian and Eulerian. Without this clear understanding, it may be almost impossible to understand fluid mechanics very clearly. So now, once you explain this for fluid dynamics, it is very important to go to the next step. That is to explain the Reynolds transport theorem. Now, most of the students will get confused with this, but it's very simple. So how to understand this is, see, when we studied our high school mechanics or our first year mechanics, students are always introduced to the flow, the movement of particles, and how the movement of particles is studied is by writing the laws of motion, the Newton's laws of motion for those particles. And our Newton's law, etc., was always written or derived for particles. Okay, so individual particles or rigid bodies, okay, however you call them. So how do you write it for the Eulerian approach? So it is always written for the body motion in Lagrangian approach. We have to change it to the Eulerian approach, and for that you have this something called as the Reynolds transport theorem. And this is something that is not taught in most of the universities in our country. But if a student has to clearly understand fluid mechanics, this concept of Reynolds transport theorem is very, very important. This is the theorem that helps us convert all the laws which have been written for a Lagrangian point of view to a Eulerian point of view. So this is crucial for all the students to understand. So let us go through this step by step. It is very simple and one need not worry so much. If you understand it in a very simple way, it makes very perfect sense. So now let us say, so in the diagram that you see, I have this solid line and this dotted line. So solid line represents a system. Now system and control volume, these two terms. The system is like a control mass system, like a rigid body. Control mass system, let us say in thermodynamics, what is a control mass system or what is a control mass? It is a fixed mass, which fixed mass in the sense that it is of a particular mass and particular identity. So each particle or each molecule and that is fixed. That means you cannot take out one molecule and replace it with another molecule and say that this is a system. So system is of a fixed mass and fixed identity. That is how we see it in thermodynamics. So here, this solid line is a system at time t, and then after a time delta t, it changes to this dotted line. So there is a system at time t plus delta t. Okay. If you have any extensive property n, so extensive property is a property that depends on the extent of the system. That is the mass, the volume, etc. of the system, the extent of the system. So it is called an extensive property. So any extensive property, capital N, I can write it as at t. Nt is nothing but n1 of t plus n2 of t. So in the time t, there are only two zones, 1 and 2. And for time t plus delta t, that is the dotted line, you have two zones which are 2 and 3. So at t, you can write this n1 plus n2 at time t. And n of t plus delta t is n2 at t plus delta t and n3 plus t plus delta t. So it's just, I'm just putting in terms of different zones or regions which have divided this into. Now dn by dt system, that is change in n with respect to time of the system. This is on the left hand side. This is called the regular derivative, which we write like df dt or dx dt, whatever we used to write from high school. This is your Lagrangian point of view derivative. So this we write it as by definition of the derivative, we write it as limit delta t tends to 0 nt plus delta t minus nt by delta t. Now, here we see that when delta t tends to 0, the system tends to control volume. 2 is like a control volume. See, when delta t tends to 0, what happens is the zone 1 and 3 become very, very small, because the dotted line will start almost overlapping with the solid line. So the region 2 will be the main region, and 1 and 3 will be very, very small regions. And 1 is like the region that is going into region 2, and 3 is like the region that is coming out of region 2. So this 2 is like a control volume in which the material in 1 goes in and the material in 3 goes out. So when delta t tends to 0, the system tends to this control volume, which is 2. Okay. So this is very important to understand. When this happens, this system and control volume can be interchanged. So we can write dn by dt system as, so this limit delta t tends to 0 nt plus delta t minus nt by delta t, I can write it in terms of different zones. The second zone I write limit delta t tends to 0 n2 t plus delta t minus n2 at t by delta t plus rate of outflow minus rate of inflow of property across the control surface. Control surface is the surface that bounds the control volume. This is a thermodynamic definition. It is not a very complex thing. But what is the consequence of this? So the consequence of this is that I have just split these two, and on the right hand side I get in terms of the control volume. So 2 is the control volume. So n2 at t plus delta t minus n2 at t. That means after a certain time delta t, what is the value of n and what it was before. If we subtract these two, what we are getting, that means that is the change that has happened in this small time within that control volume of this property. Okay, whether it has increased or decreased, we don't know. It is a change. Okay, and that is one part. Second is this 1. If it is tending to 0, this 1 zone goes into 2 and 2 is going into 3. That means rate of outflow minus rate of inflow. So rate of outflow minus rate of inflow will stay back. So if I give 10 rupees to someone, okay, and I get 5 rupees back, then rate of outflow minus inflow means what I'll be at minus 5. I've given 10 rupees to someone, whereas I got only 5 rupees back. Right? So that is what is remaining with me. So that is what is rate of outflow minus, why it is outflow minus inflow. So what is remaining is outflow minus inflow of the property across the control surface. Okay. So once we understand this, we have to write what is this outflow minus inflow across the control surface. So here I have drawn this control surface, an arbitrary imaginary control surface of elemental area dA. Okay, and eta cap is the unit outward normal vector to that elemental area, and v is the unit vector outward. The velocity of the fluid that is going through out of the control surface. So v dot eta. Okay, if you take the dot product of the outward normal and the v velocity vector, you get the velocity component in the outward direction, that is, which is going out of the surface. So v dot eta, that is the velocity component which is going in the which is going out of the control surface, that is in the normal direction. So v dot eta into dA, velocity into area, we all know that this is the flow rate, volume flow rate. So A1, V1, A2, V2, we do know. So V dot eta is just, it doesn't have any unit as such. It is just a unit vector. So V dot eta dA is nothing but the flow rate, volume flow rate. The volume flow rate into rho is the mass flow rate, and this n is the intrinsic property, which is n per unit mass. So the mass flow rate into the n will give you the sorry, this is not n actually, not capital N. So the mass flow rate into the small n is nothing but the property flow rate. So that is the property flow rate of inflow and outflow. For inflow and outflow, we don't have a different value, because if it is inflow, then V will be towards the inside. And if it is outflow, V will be towards the outside. And anyway, when you do the dot product with the outward normal vector, eta, it will automatically adjust the sign, whether it is inflow or outflow. So therefore, dn by dt system, I can write it as this part, limit delta t tends to 0, n2t plus delta t minus n2t by delta t. This I can write as del n del t cv plus rho into n v dot eta dA. Anyway, rho in n v dot eta dA we have understood. Why partial derivative? Why not full derivative for dn by del n by del t cv? That is a very important question that always students will ask. So why it is like that is because when we take the total derivative, we move along with the particle. So along the space. Here we are fixing a region in space, and we are not moving along the space. We are only at that location. What is the change with respect to time that we are seeing? Therefore, it cannot be a full derivative, but rather a partial derivative. If we take the full derivative, that means just like we wrote dp as del p del x dx, del p del y dy, del p del z dz. We will have to write that for this if it is moving along space. So because we have fixed the control volume, that is the region 2, therefore we have to write it as a partial derivative. So this is your Reynolds transport theorem in the most simplest form, this expression, and that is about it. It is more conceptually strong rather than mathematically. Mathematically it is quite simple. Conceptually it is a little bit tricky, but once you understand, it is very, very, very straightforward. Excuse me. So we will apply this for continuity equation, and once we do that, we will stop. Why we need continuity equation? We'll see. So let n is equal to m. M is nothing but the mass of the system. So therefore, small n will be m by m, which is 1. So dm by dt system is equal to del m by del t cv plus rho into 1 into vr dot n dA. Vr equal to v if cv is stationary. So here, when I talked about this velocity of the fluid going out of the control surface, if the control surface itself is moving, then you have to take the relative velocity between the fluid and the control surface. Okay, so therefore I am writing it as Vr as relative velocity, and Vr equal to v if cv is stationary. That is anyway straightforward, because velocity of cv is 0 means there is no relative velocity except the velocity of the fluid itself. So now once we understand this, mass of the system is fixed. What does this mean? See, from thermodynamics, we know that control mass system is you cannot change the molecules, you cannot remove the mass and all. So mass of a system, control mass system, is fixed. So it cannot change in any way. So obviously that means dm by dt system is 0. So the left hand side is 0. Okay, so that's why we never use conservation of mass in solid mechanics as frequently, because there is no meaning for that, because we, by definition itself, we have fixed it. So now we see the left hand side I have set it to 0. The right hand side is del m by del t cv plus rho v dot eta ds over the control surface. Now m I can write it as integral rho dv. So mass into the volume. So integral of density into the unit volume over integrated over the entire control volume will give you the mass. So del m by del t CV, I can write it as del by del t of rho dV. So for a non-deformable control volume, I can take this integral out because V does not change with time. So if velocity, the volume of the control volume changes with time, then I cannot take the derivative into the integration. I can take it into the integration provided I have some extra terms which can correct that change of volume with respect to time. But here I am taking that control volume to be non-deformable. So therefore, I can take this del m by del t CV as I can write it as integral CV of del rho by del t into dV. Similarly, the other term rho v dot eta dA, I can write it as over the control volume. So a surface integral, I can change it into a volume integral by using the Gauss divergence theorem. So this is a very common theorem in mathematics, which is normally taught to the students. So Gauss divergence theorem, if you are very interested, you can go through any of the mathematics book like Krissig. There you will get this. So you can use this theorem directly. So I can convert the surface integral to volume integral by using the divergence. So divergence of rho v dv. So then I can just combine the two. 0 as del rho, 0 equal to del rho by del t dv plus over the control surface rho v dot eta dA, and I can combine these two to write over the control volume del rho by del t dv plus divergence of rho v dv equal to 0. And you see that the quantity inside the integral, this inside the bracket, this is equal to 0, and this you know as the continuity equation, many of you. Now, if I say integral of something is 0, does it mean that whatever is inside is 0? That is a very important question. So every time I go to a fluid mechanics class or any other class which has this thing, student will ask me, sir, how are you putting that, the inside quantity is 0? I ask the student, you tell me how you know that, how can you say that quantity inside is 0 if the integral is 0? Then I also give them another clue. I confuse them. Suppose I tell them, you take integral 0 to 2 pi of sin x dx. Is it 0? So I'll go here, see, continuity equation. So if I take minus pi to pi integral sin x dx, it is 0. Right? So if I take from integral 0 to 2 pi sin x dx, it is 0. Fine. What if I integrate from 0 to pi by 2 sin x dx? Is it 0? Then the student will say no. But then how can I say the quantity inside is 0? So the quantity inside is 0 because see here the integral depends on the limits. In the quantity here, this control volume we say, but we have not defined the control volume. What is the control volume? We don't know. We have not particularly defined whether it is rectangle or square or triangle. Nothing we have defined. So since this thing itself is arbitrary, so a function whose integral is 0 for any arbitrary limits means that function itself is 0. So that is how I give that point to explain to the students. So therefore, the quantity inside is 0. It doesn't depend on any limit. So obviously, if it is depending on a limit, that means the inside quantity need not be 0. But here it does not depend on the limit, therefore the inside quantity is 0. So therefore del rho del t plus divergence of rho v is 0. And this is the continuity equation because CV is arbitrary. That means the limits are arbitrary. We are not fixed any particular thing as the limit. So this is the way we can use this Reynolds transport theorem to convert Lagrangian view to Eulerian view, and showing this continuity equation because in Lagrangian view we never have something like conservation of mass because we are not bothered about it, because automatically by definition itself it is happening. But here we need to have a conservation of mass specifically because it is not happening directly. So therefore we have the continuity equation. Similarly, you can derive the other equations for from Lagrangian to Eulerian, like Newton's second law itself. There is the balance of forces or momentum, etc. So maybe that becomes a little more complex and tedious. And I have actually derived the entire Navier-Stokes equation in the advanced fluid mechanics class, and usually it takes like 3 or 4 classes of about 45-50 minutes each to completely derive the entire equation. Usually a 1 week or 1.5 weeks goes in just deriving that. But it is an exercise that students seem to enjoy, and as the things get clearer and clearer, they are more happy. So you can it can be done using the Reynolds transport theorem, or it can be done from the first principles also. So with this, I think example, I think I'll stop. If you have any queries, we can have it for a few minutes session of queries. So let me know. I know it was a very long lecture, and fluid mechanics is afternoon session is a little difficult.
Thank you so much.
Yes, sir.
So thank you. Just let us look into the Q&A session. Is there any questions? Swapna, are you online? Swapna, you can.
Sir?
You can look into the question Q&A box, and you can ask the
Okay,
questions.
sir.
I think most people might have slept off. Happens in.
The question is asked by Justin Regimon. Sir,
Okay.
is the fluid balls concept the only way to study fluid motion, or there is any other way to study the motion?
Which one?
Fluid ball concept.
Fluid ball. Okay, particles or something. Okay. See, fluid motion can be studied in many ways, but the classical way that we follow in our engineering is the classical continuum mechanics, the fluid mechanics. In that, we use this concept of fluid particles, which is similar to what we do in solids, where solids have a finite size, but we say it is a point mass. A point cannot have a mass because the point is technically zero in size, zero volume. It cannot have a mass. Even if density is infinite, it has to be infinite to have a mass. So we take a point mass, means we have a finite size which is very small, so we consider it as a point. Similarly, here the fluid particle is of a finite size, but for mathematical point of view, we consider it to be a point. But physically, it is having a finite small size. Hope that is clear. I request you to go through that article link that I shared on this one. Hope you have noted it down.
Thank you, sir. The next question asked by Rahul Kumar. Is Pascal law valid for only static fluid? Is Pascal law has effect on flowing fluid also?
So, see, when we say that the Pascal law is valid for static fluid, what does it mean? The tau, that is, the fluid is not deforming. So, if fluid is deforming, then Pascal law you cannot use. There is something called rigid body motion. For rigid body motion, there are many textbooks which are there. So, based on this idea that there is no shear stress, you please go through those topics within textbook. So, what I suggest is, see, foreign author maybe difficult for most of us, but Bansal is no good. So maybe you can go for this book, Fluid Mechanics by Som Biswas and Chakravarti. So this is a very good book, and it is easily available in India. So it gives you very good detail of all these topics, and very nice insights it gives into where what happens. Okay, so remember, it is fluid at rest here. Specifically, I say where fluid is not deforming, that is the shear stress is zero.
Thank you, sir. The next question from Ambrose. Why do mechanical engineers have to study fluid mechanics?
Okay, this is I mean, if you don't know, okay, if I say what is core in a mechanical engineer, maybe the heart of mechanical engineering is something like an IC engine, and in IC engine also there is a fluid flowing in and there's fluid flowing out. So you have the air fuel mixture flowing in and the exhaust gas flowing out, and then there is work done. So without that, of course, without fluid mechanics, you will not be able to understand any of it. So of course.
One second, sir, sorry that interruption.
Yes,
sir, one has come online. Sir, please mute your mic. Mute your mic.
You want me to mute my mic?
So no, sir. Mr. Rohit has been allowed. So Rohit, you have been allowed to ask questions, sir. So mute your mic, or if you want, you can ask the question to sir. Mr. Rohit. Sivaraja, you have been allowed to come into live to clarify your doubts with Kaushik sir. Since Rohit, you are unable to answer, so I am cutting down. Rohit, are you online? Sir, please go ahead, sir. Please, sir. Sorry for interruption, sir.
That is what. If heart of mechanical engineering is IC engine, say, then obviously fluid mechanics is very, very important. Okay, and even say you have gears, in which you have lubrication where fluid is used, and so without fluid nothing is complete, isn't it? So that's why we study fluid mechanics for mechanical engineers. It's one of the core subjects. Turbo machines, you have turbines, pumps, compressors, etc.
Thank you for your explanation, sir. The next question from Ashish Kumar. Okay. What is physical significance Navier-Stokes equation?
Okay, so see, Navier-Stokes equation is actually nothing but the balance of, or when you write Newton's second law, okay, which is normally written in Lagrangian point of view, when you write in Eulerian point of view, you get the equation of equilibrium, Navier's equation of equilibrium, where you have the mass into acceleration on one side, that is rho into du dt, or whatever you have. That is actually mass into acceleration. Everything is per unit volume because it's a fluid. It's always easier to express per unit volume. And on the right hand side, that is nothing but mass into acceleration is what the net sum of all the forces is mass into acceleration. That is Newton's second law. So on the right hand side in Navier-Stokes equation, you will have one is called the viscous force. That is the surface force that is acting. So viscosity is the shearing of the two surfaces. So that is one term. And then you have the body force, that is rho into g term. And of course you have a pressure term, that is also a surface force. So surface force will be resolved into the shear forces as well as the longitudinal forces, that is the pressure. And you have the body force. That is your essential Navier-Stokes equation. So I request you to go through that book, Introduction to Fluid Mechanics and Machines. Okay, and it is very clear in that, and it's very easy to understand. It takes a little bit of time, but definitely it is possible to understand.
Thank you, sir.
We'll take one question. Please make it. Sir, let me ask. Sir, Mr. Rohit had asked one question.
Okay.
Sir, can you explain one practical case of Navier-Stokes equation?
Practical case.
Yes.
See, Navier-Stokes equation is valid for any Newtonian fluid flow. So practically, the flow through a pipe can be addressed by Navier-Stokes equation. The flow through channels can be addressed. The flow over a surface can also be addressed. But those concepts, it cannot be immediately, given. There is a little bit of a derivation. But yes, practically, you can use it to address any of these problems.
Okay. Thank you, sir. Thank you so much. And sir, sir, thank you so much, and thank you so much for a wonderful lecture. And I used to say, since I have worked in both NITs and NIT and private engineering colleges, I used to say to others, the way how the IITs, NITs, and IIC differs from the private institutions. So even the Reynolds transport theorem is not introduced in the fluid mechanics syllabus, and mostly like the difference between Lagrangian and Eulerian is not explained properly to the students. Because of this lagging, the students may not be able to see the fluid mechanics in mathematical point of view. So the lagging is still there. So I hope this lecture will enhance the understanding of the faculties, and which will help them to go for a perfect teaching classroom, and of course this will help them to enter into research in fluid dynamics also. Because for fluid dynamics, these are the basic equation which needs to be understood to execute their to mimic any physical behavior of fluids or something else. So certainly this will be very much highly useful, sir. And thank you so much for your time, and you have prepared very good these things. And certainly, thank you so much for being with us. And
I hope the presentation was clear, because normally in class I don't take any presentation. I do on the board.
Yes.
That is more easier and it is more effective. So I try to replicate that by writing it by hand and scanning it.
Yeah, yes. If you do that in that way, there is good. And presentation is either. That's why I'm saying the presentation is very different. So normally it might be typed and the equation might have been copied from some other textbook, because we are unable to type. It will take much time, So that is the usual practice of the experts while doing that. But this seems to be very different. So you have written the paper and you have made it in these things. It was nice. And thank you, sir. So if time permits, we will have one series of lectures in this fluid mechanics, which can help the faculty members to understand further, sir. Thank you so much, sir. We will meet in some other occasions. Thank you. Nice to see you, sir. Thank you. Thank you, Sopna. Dear friends, thank you so much. So this is how the fundamental of fluid mechanics has to be taught. But of course, since we are in the private engineering colleges, so we need to teach the students to score the marks, and we are making them to solve the numerical equations, and we are not concentrating the fundamentals. So the fundamentals has to be taught in this way, I believe. Since while I was in NIT, I used to handle the advanced fluid mechanics and these things, computational fluid dynamics, and this is how the NITs, IISc, IIT differ from the other private colleges. And the syllabus also, we mostly do not concentrate on the derivations. So we should make the students to extract the physics from the mathematical equations. So if only this is being done, this will be highly useful for the students when they go for higher studies and they will move to abroad. So I heard from my students. So I used to, as I said, I used to teach fluid dynamics. So students, most of the students are doing masters in fluid dynamics, and some of them are doing PhD in fluid dynamics also. So they used to say, sir, the fundamentals what you have taught is very highly useful to understand in the content what we are doing now. So that I used to teach the fluid mechanics and this in the mathematical point of view, and sometimes I will make them to extract the physics from the mathematical equations. So this is how we need to teach. But however, in periodic analysis, it is not possible, I believe, because we have to throw the derivation, the important derivation, and we need to make them familiar with the numerical problems. So hope certainly this lecture will change your classroom teaching, and certainly this will be useful for those who want to go for research in fluid dynamics. Thank you so much. We will see tomorrow. And however, so the quiz can be attempted between 5 to 6 for the thermodynamics as well as the fundamentals of fluid mechanics. And the questions will be very fundamental. So with the understanding of what you have learned from these two lectures will be highly enough to attempt these things. And those some of you who have not joined still in WhatsApp, and some of you have not filled the form. So I request you to fill the form for the certificates, because we need to make various certificates. If only we start to prepare certificates, at least it will take 1 week to prepare the certificates. So if you give the correct data, so as soon as it is over, so we'll start to prepare the certificates. And thank you so much. We will meet by tomorrow. And tomorrow's sessions, on morning session, will be handled by Dr. S. Venkatachalapathy, professor from NIT Trichy. He will be handling on fundamentals of heat transfer. And in the afternoon sessions, will be handled by Dr. V. Arunmozhi, associate professor from NIT Trichy, and he will be handling the fundamentals of thermal engineering. Hope these two sessions will be very wonderful, and we will meet by tomorrow morning. Thank you so much.